Hi everyone, I'm Moithira Chatterjee from UIUC, and today I'm happy to present our work Sound2Sight for generating visual dynamics from sound and context. This was a joint work with Anup Cherian at Mitsubishi Electric Research Labs and Professor Narendra Ahuja at UIUC. Let us consider this video. We see a few frames and hear the audio after that and can probably guess what happened in the occluded frames. While this task might seem obvious to humans, the same is non-trivial for computers. Guessing the missing data of a modality is critical for intelligent decision-making. Thus, in this work, our task is to hallucinate the missing video modality from other cues such as audio. Our key contribution is as follows. We study the task of future frame generation from audio conditioned on the visual past. We propose Sound2Sight, a novel, deep, multimodal variational autoencoder to address this challenge. Our model shows state-of-the-art results across 3 audiovisual datasets, including 2 novel ones. Our model consists of the following key components: a prediction network, a multimodal stochastic network. The previous 2 components taken together constitute the generator part of our network. The final component of our model is the multimodal discriminator network. The details of each of these components are introduced subsequently. Let us now delve into the details of the prediction network. The prediction network takes as input the previous frame, a stochastic noise vector Zt sampled from an appropriate distribution. With these sets of inputs, it generates a prediction of the current frame. This estimated frame is then compared against the ground truth by a mean squared error loss. We implement the prediction network using an LSTM followed by a stack of deconvolution layers, the mathematical representation of which is now shown. We now describe the multimodal stochastic network, which is responsible for estimating the aforementioned distribution from which Zt is sampled. The stochastic network is tasked with computing a distribution called the prior from which Zt is sampled. This distribution takes as input acoustic transformer embeddings from time 1 to t and visual transformer embeddings from the past, that is from time 1 to t-1. Now, to train this network, another distribution called the posterior is learned. The posterior network is similar to the prior in design, except it accepts visual embeddings of the current frame as well. These distributions are then matched via their KL divergence. During inference, it suffices to use just the prior, and hence our model can work with only the visual embeddings from the past and the audio input embeddings. The overall generator loss is now shown. We will now talk about the multimodal discriminator network. The multimodal discriminator network couples a standard classifier with a LSTM-based one. This module, besides looking into the realism of the synthesized frame, also judges whether the synthesized videos preserve motion regularities or not. Further, it also determines if the audio and the synthesized visual streams are in alignment. The mathematical representation of the multimodal discriminator network is now shown. We conduct experiments on 3 audiovisual datasets. The first one is called the Multimodal Stochastic Moving MNIST with a surprise obstacle. The details of this dataset are introduced subsequently. The next one is a set of videos from the drums class of the existing audio set data. The final dataset consists of a set of newly introduced painting videos crawled from YouTube. We conduct frame generation experiments on these datasets where we show a certain number of frames from the past to set the visual context and provide the input audio corresponding to the past and the current frame as input. The task of an algorithm is to generate an estimate of the current frame given these inputs. Let us now talk about the details of the construction of the novel M3SO dataset. The M3SO dataset associates all 10 MNIST digits with a unique tone of a certain frequency. The dataset features videos where a digit moves in a box in rectilinear trajectories, except upon collision with the box boundaries when it switches to a random direction of motion. We introduce an obstacle at a previously unknown spatial location in the unseen frames. When the digit collides with this obstacle, it also switches to a random direction of motion. Upon the digit's collision, the frequency of the tone changes momentarily. This is shown in the plot here. The amplitude of the tone is inversely proportional to the distance of the digit from the upper left corner of the screen. This is shown in the plot at the bottom. Experimental results show the superiority of our method over competing baselines as measured by SSIM, as well as by PSNR. Next, we show some sample generations by our method versus competing baselines on all datasets. Thank you for your attention. Please look up the paper and the project page for more details. Thank you.